We're going to finish up talking about amino acids and peptides, get into a little proteins. The last time we started talking about this, we talked about structure, we talked about the Henderson-Hasselbalch equation, and we talked about pKa's and of the different groups, and we talked about the isoelectric point. So today we're going to talk a little bit more about alpha amino acids. Now there are a variety of amino acids that you can actually make. Alpha amino acids are the ones that are most biologically relevant. There are other types of amino acids like beta and gamma and delta amino acids. What makes an alpha amino acid an alpha amino acid? The amino group is on the alpha carbon, and the alpha carbon, right, is the carbon directly attached to the carboxylic acid. And so you can imagine having a variety of different types if you have the amino group located in different places. But for the purposes of this, and for most of what you're going to learn about in biochemistry when you get there is all about alpha amino acids. What version of the alpha amino acid is the most prevalent, the L or the D? L. And L all have the S absolute stereochemistry with the exception of which one? Cysteine, that's right. So cysteine, having a sulfur, the priorities change, and it actually has the R absolute stereochemistry. These are the building blocks, or as our friends in polymer science call them, these are the monomers, right, that we actually can use to build up these biopolymers that we call proteins and peptides, okay? All of them are chiral molecules with the exception of glycine because R is a hydrogen for glycine. So glycine is a very versatile amino acid because there's no stereochemical issues with it. It has no chirality, okay? As you might imagine, you can have L and D. We've talked about that a little bit before based on D and L is all about relative stereochemistry, not absolute stereochemistry. It's an old way of naming things, but biochemists, for whatever reason, like to stick to the old nomenclature. I've never figured it out. But L-glyceraldehyde has this stereochemistry, and if the amino group, the carboxylic acid, and the side chain, if you will, kind of match up like it is for L-glyceraldehyde, we call it an L-amino acid. But it doesn't tell us whether it's R or S, okay? But L-glyceraldehyde actually has the S configuration at the alpha carbon as well. So I prefer to talk about R and S. For some reason, biochemists and biologists like to talk about D and L. But D and L is a outdated nomenclature system. Acid-base properties of amino acids, we've talked about this. The amino acids, if we take an amino acid and place it in water, we are not going to have it look like this, right? Because we have a carboxylic acid which has a pK of around where? Yeah, 4 probably a little high for these, but it's below 7, right? So 2 to 3 for many of the carboxylic acids that we see in amino acids. The amino group is going to have a pKa of around where? Yeah, up at around 9, 10, something like that. So I have a pretty strong acid. I have a pretty good base. They're going to react with each other, right? And we form these viterionic forms. And these viterionic forms, as we talked about before, right, are overall electrically neutral. They don't move in an electric field, right? And so we can't separate them in this form based on electrophoresis that we talked about yesterday. Fact is, we know this equilibrium lies quite to the right. What happens if we take this amino acid and water and we add sulfuric acid? What's going to be the charge on the amino acid? So I take and I add some sulfuric acid, bring the pH down to, let's say, 1. What's the charge going to be? Positive. And if I add some sodium hydroxide and bring the pH up to, say, 12, it's going to be negative. So we can change the charge on these amino acids by altering pH, and that's why we were talking about the Henderson-Hasselbalch equation the other day. And again, that's an equation that you'll need to remember when you get into biochemistry, or if for those of you going on to analytical chemistry. It'll come back to haunt you there as well. So if you look at an amino acid, right, we place it under acidic conditions. The base picks up the proton, and we have a positively charged amino acid. Likewise, if we treat it with base, the acid gets deprotonated, and you end up with a negatively charged amino acid. And we can separate these based on electrophoresis. We talked a lot about that last time. However, if you look at other amino acids that have side chains that can actually be ionized, that becomes a little different. So what would be the overall charge on this amino acid at pH 12? -1, -2, +1, +2? It'd be -2. At pH 12, this would be deprotonated, but so would this, right? We would have overall charge of -2. What about lysine? If we took it up to 12, what would it be? It'd be -1. If we lower the pH, let's say to 1, it would be +2. So you can see you can have very different charges on these amino acids depending on pH. And we're just talking about the extremes here. You'll learn about the details more when you get into biochem. Okay? So peptides are small polymers of amino acids. The difference between a peptide and a protein is somewhat arbitrary. But the general rule is that we consider something a peptide if it has 50 or fewer amino acid residues linking it together to make a peptide. Now, does that mean that if all of a sudden you had something that was 51 that people would start calling it a protein? Not necessarily. Typically, we think of proteins as containing hundreds of residues. Okay, so there's not really an exact line at which you stop calling something a peptide and start calling it a protein. But the generally accepted range is up to 50 amino acid residues. Okay, and so when we get much larger than that, we start calling it proteins. By convention, we always draw peptides starting from the N-terminus and go to the carboxylic acid terminus. So remember, we've got an amino acid that has a nitrogen and a carboxylic acid. We will draw that nitrogen here for the first amino acid residue. We will make the polymer, and it will end at the carboxylic acid terminus. So we write them from N-terminus to C-terminus. This is an example of dipeptide because we've got two amino acids linked together. They're both, one of them is glycine, and one of them is alanine. So this is glycoalanine. Nobody likes to say that. We just call it glyala, right, or GA. Depending on which letter codes you'd like to use. So is glycine alanine the same as alanine glycine? It is not. They have different residues at the ends, right? It would be flipped. So it's not like adding 1 + 1 or 1 + 2 is 3, just like 2 + 1 is 3. It isn't the same. Okay, so. Here's a tetrapeptide. What's this residue? That's glycine. What's this residue? It's got the alcohol. Which one is that? Serine. What's this residue? That's a benzyl group. That's phenylalanine. And then this residue is? It's glycine again, right? So this is, if you wanted to really give it a name, glycylceryl phenylalaanyl glycine. Nobody says that. Glyceraphy gly. Think about how many different ways we can take these 4 amino acids and couple them together and get different polymers. It's quite a few, right? We don't need to actually do the math to do it. This is what it would look like with your model kit. By the way, you don't have enough pieces in your model kit to build even a small peptide like this. Okay, but you can see the N-terminus is a glycine. The C-terminus is also a glycine. And so you can see the different residues shown there. We know that the peptide bond is quite strong because of resonance, right? And it's actually to our benefit that we actually have peptide bonds. They're strong. They hold up to water. Think of nylon, for those of you in polymer science. Nylon is quite robust. You use it to make ropes that are going to be exposed to weather. And the reason you do that is because it holds up well, right, to harsh environments. You do not use polyester rope on boats. You use polyamide rope on boats, right, because polyesters will degrade a lot faster. And so we are, for all practical purposes, we are nylon-based life forms, if you want to think of us like that. We know that the resonance structures put some double bond character between the carbon and the nitrogen. And even though this is a minor resonance contributor, it is still significant. There is restricted rotation around that carbon-nitrogen single bond because of it. And you can actually tell that in the NMR. You can tell that you have two groups attached to the nitrogen quite clearly because of the restricted rotation. They don't average out. Because the carbonyl is what hybridization? It's sp2. The amide bonds turn out to be quite planar. So you have these planar groups within a peptide structure, and that helps overall give it structure. So the amide groups have to be planar. And so because we're dealing with all L amino acids in this case, if you drew out the chain linearly like we have here, there's the glycine, right? There's the final glycine. You can see that groups actually end up being on opposite sides of the chain to have the correct stereochemistry. The other type of covalent bonds that we have to pay attention to in proteins and peptides are the disulfide linkages. So two cysteines can actually come together to form a sulfur bond, right? What amino acid residue did we learn about last time that actually has the sulfur bond? Cysteine, right? And so this is a cysteine unit. So the cool thing about this is you can have one peptide chain that goes from N terminus to C terminus. You can have a completely separate peptide chain that's not even linked to it, or it could be. And then you can have these disulfide bonds that actually put in some secondary structure. And that's kind of cool. And it turns out that you can take cysteine, or any thiol for that matter, and you can oxidize it to the disulfide. What's the product of the oxidation other than the disulfide? What's the other byproduct? I'm taking off two hydrogens, and what else if I'm oxidizing? You do, you get water. So we can oxidize the disulfides, or oxidize the thiols, and get disulfides. We can also reduce the disulfide back to the free thiols. And this turns out, everybody, to be very, very important if you like to go and get your permanents and whatnot in your hair, right? It turns out that our hair is cysteine rich. For those of you who have curly hair, you have curly hair because you have certain disulfide bonds that make it curly. If you have straight hair, you lack those disulfide bonds being in that order. We all have disulfide bonds, but it depends on how they're ordered. So if you have straight hair and you want it to be curly, what do? For those of you who've ever had this done, what do? Do they curl it first? They place a solution in your hair, right? And what do they call it? They call it a perm? They should be calling it something else. They put a reducer on to start with. So what are they doing? They put a reducing solution and it stinks because it's a sulfide. Not yet. It's a reducer. So what are they doing? The reducer breaks all the disulfide bonds and opens them up, right? Then what do after they put the reducer on? Now they put it on curlers or whatever, right? Whatever they use. I don't know what they use, okay? Then what do after they've got it on this little mechanical things to give it the shape they want? Now what do we have to do? We got to reoxidize. So they add the oxidizer. They add an oxidizing agent that actually reforms the disulfide bonds. But now since it's on a physical, the disulfide bonds get formed differently. And so that's why it's a permanent, okay? Because these are covalent bonds. Of course, your body doesn't make them like that, so it will eventually grow out, right? And so you have to, keep getting your hair done or whatever to get your permanent. But that's how permanents work. And so the smell that you smell in the beauty shop is the reducing agent. I mean, it's a thiol. It stinks. But it reduces the disulfide bonds to the free thiols, like we have here, allows the hair to straighten. They then put it on whatever thing they want to get a shape of, and then they put on an oxidizer and reform the disulfide bond. So that's how that works. If you want to straighten it? If you want to straighten it, yeah, you can just use the reducer. And they can chemically straighten your hair. Huh? Hair's not that, I mean, it grows. Right? This is a large, fairly large peptide. Obviously, you don't have enough model kit pieces to build this one. But notice the N-terminus has a cysteine. What's this one? What's this one? This one? And notice it's not a carboxylic acid. It's actually a C-terminal amide. Okay? This is called bovine oxytocin. Anybody know what it's used for? Bovine is cow. Yeah. Anybody know what oxytocin is? Huh? Actually, it does have something to do with amore, but huh? It's not a painkiller. Actually, one can argue that it's actually a pain inducer. Has anybody ever heard of Pitocin? Has anybody ever known anybody that had to have their labor induced? They use Pitocin, and Pitocin is nothing more than oxytocin. It's just a brand name, okay? It was actually discovered from bovine, yeah, but they synthetically make it now. And so it turns out that this causes the uterine wall to contract, and so to help increase, the birthing process, or to get that going. You got to have this disulfide bond, though. If we reduce this, it doesn't work. It's got to have this particular structure. And notice it's got this loop structure here, which kind of makes it look more globular. If we were to reduce that, it would take on a more linearized structure and not have any activity whatsoever. So this disulfide bond is actually quite important in this particular peptide. It does, yeah, so it'll form a loop there, yep. Now you can actually have disulfide bonds that connect different strands that don't actually form a loop. Mm-hmm. Here's an example of conotoxin. So for my marine biology friends, what's conotoxin? It's actually a very strong neurotoxin. It's a big macrocyclic molecule, right? So we've got quite a few amino acids, but we also have two loops in this particular structure. We have a loop between cysteine number 2 and cysteine, let's see, 3, 4, 5, 6, and cysteine 7, and then between cysteine 3 and 12. But you can imagine having a loop here and here, or here and here and here and here, right? But it's got to be these loops for this to actually function as a neurotoxin, okay? And so this fish hunting cone snail actually uses this to paralyze. Thank you. It paralyzes the fish so that they can consume the meal, right? It's life, you know. I didn't do it. It's got to eat too. That's right. But this is chemical warfare right here, right? I mean, this is a neurotoxin that's actually quite potent. So you don't want to play around with this snail. It'll kill you. And it'll kill you using a very, very potent peptide. Okay? That's what its structure looks like when you build it with your model kit. Pretty complicated. We don't have enough. That's right. Now, how do we determine the structure of a peptide? Right? I gave you the structures of those peptides, but we didn't really know what they were until we actually analyzed for the structure. How have we determined structure in this class? IR, NMR. How else have you determined structure? What other properties have you used? You've used melting point. We could determine through optical polarimetry type means. It turns out that this is an extra layer of complexity, okay? Because you're dealing with such large structures, NMR gets really messy. NMR is useful in the analysis of these things, but you've got to have more than just an NMR analysis usually to figure out what it is. And the first thing that you do is you figure out, well, what amino acids make up the structure? So you do what's called an amino acid analysis, and that is you take the molecule and you chop it up into just its basic amino acids, and you see what amino acids are present. Once we know what amino acids we have, we know what building blocks we're playing with. Not all peptides will have all 20 amino acids, right? So if I know that my structure doesn't have proline in it, or if my structure doesn't have a proline, I better not put that into my structure, right? So we can think about it that way. We also do what's called terminal residue analysis. We need to figure out what's on the ends. What's the N terminus and what's the C terminus? I need to know where I'm starting and where I'm ending, right? I know what the building blocks are, but I got to know where to start and where to end. So let's suppose Gabriella gets an amino acid analysis and she finds out that there's 5 amino acids that make up this peptide she's studying. But which one of those 5 starts the sequence and which one of those 5 end the sequence? She needs to know that information because we've got to write it out from N terminus to C terminus. So we need to know what's on the termini. Okay? The way that we can do N-terminal analysis is by a process called Edman degradation, which you'll learn about in biochem. I'm not going to spend a whole lot of time. But what you need to know is that it will remove that N-terminal amino acid through an organic chemical reaction. And it's kind of a slick reaction. And it just removes that one amino acid. And you can then use HPLC and you can determine what the amino acid is. Okay? You can also do C-terminal analysis where you're using this enzyme called carboxypeptidase, which means it only functions on the C-terminal residue of a peptide. Exactly how it does that, I don't know. But it's an enzyme that does it very selectively. It will clip off that C-terminal amino acid. And then you can isolate that amino acid and analyze it for what it is. So at that point, after we do an Edman degradation, we do a C-terminal analysis, we know what the starting and ending points are for our sequence. And we know what the building blocks are in between. What don't we know now? Yeah, we don't know anything about how things go in together. I just described to you the 2 easiest parts of the whole thing. Because all you do for amino acid analysis is you boil it up in acid and completely hydrolyze the protein, and you get all the amino acids, and you just analyze. Oh, and Yusuf finds out there's 5 amino acids in this protein, 5 unique amino acids. But he doesn't know, are there 6 lysines, and he just knows that there's 5 unique amino acids. Terminal residue analysis, Gabriella figured out what was on the N terminus and what was on the C terminus. But now Aubrey has to figure out what's in between and how it's connected together. And that's the tough part. And that's really difficult. And the way that we do this is by what's called partial hydrolysis. Because imagine taking a peptide that, let's say, has 60 residues in it. Right now, all we know is that it's made up of certain amino acids and what the N terminus and the C terminus are. That's all we know. Right? And so we got this big peptide that we have to figure out the sequence for. Well, big things are kind of difficult to deal with, right? So let's deal with smaller things. So what we do is we do what's called a partial hydrolysis. We take that big peptide and we break it into smaller fragments. And there are some enzymes that do this for us. Okay? And you will learn a lot about this in Biochem 1. Trypsin, so you'll take your peptide and you will treat it with trypsin, which is an enzyme that will cleave your peptide at the lysine residue and at arginine residues. It will not hydrolyze anywhere else. Okay? Another enzyme that you can use is called chymotrypsin, which will cleave at phenylalanine, tyrosine, and tryptophan. What are tyrosine, phenylalanine, and tryptophan? How are they related? They're all aromatic. Let's say that, okay? Yeah, so they're all aromatic. What does lysine and arginine have in common? They do. But the important thing is that at physiological pH, lysine and arginine, the side chains, are both positively charged. So trypsin likes to cleave the positively charged things. Chymotrypsin likes to cleave at the aromatic things. Pepsin will cleave at a variety of other residues. And cyanogen bromide, which is not an enzymatic reaction, actually only cleaves at methionine. So these are what we call the cleavage rules. Very important when you get to biochem, because they're going to give you problems where they ask you to figure out what the structure of a peptide is, giving some data from peptide cleavages. And so you have to, I remember doing that when I was an undergraduate in my 2.5-hour biochem exam, trying to figure out the structure of one protein. That was one question exam. Give the structure of this protein with this data. It took about 2.5 hours to solve. Okay? I got partially. Yeah, I probably got about a 70 on the exam, which was pretty good. So once we have these smaller fragments, then what we do is we determine the sequence of those fragments using what's called successive Edmond degradations. What does the Edmond degradation give us? The N-terminal residue, right? So imagine I've got a peptide that has 4 amino acids linked together that I got from, I don't know, let's say trypsin cleavage, right? If I do Edmond degradation, I can figure out what that amino acid is, right? Then I take this 3 and I do it again, and then I can figure out what that one is, and I do it again, and I can figure out what that one is and that one. And so then I can link them together through the successive Edmond degradation. But I can only do successive Edmond degradation on small fragments. I can't do it on the entire peptide, because by the time I got past 4 or 5 residues, because you have losses in all of these things, you wouldn't have much material left to work with. Because remember, yields are never 100%, and the more steps you add to a synthesis, if you don't have a perfect yield, your amount of material you have goes down and down, right? So we have to break this up and do this only on small peptides. Okay? So let's look at a sample problem. I do not expect you to be able to do this on the exam. Okay? Not in this class. You'll have to do it in biochem, and I'll let them torture you with it. Okay? But let's look at a simple example. 20 amino acids can be done no problem this way. But this is just to kind of give you an idea of how this goes. So Dane figures out by amino acid analysis that there's 2 glycines, 4 alanines, 4 leucines, 3 phenylalanines, 1 tryptophan, 2 lysines, 2 methionines, 1 serine, and 1 arginine. That's what he knows. So he knows what amino acids are there. He knows approximately how many. But he doesn't know anything about how these are put together, right? So what does he do next? All right, we do N-terminal residue analysis, and C-terminal. And so what do we use for N-terminal analysis? We do the Edmond degradation, which has a reagent. And he determines that one of the alanine residues is at the N-terminus. So he knows where that is. So he knows we're starting with ALA. And then he knows by C-terminal analysis that the end of this thing ends in a phenylalanine. Now what he's got to figure out is what's in between, right? How do we do the C-terminal analysis? Carboxypeptidase. That's right. So this right here would take him about a full day using this type of technique. Not very efficient. That's why back 50 years ago, to figure out the structure of conotoxin, that was a PhD dissertation. Today we can figure out the structure of conotoxin in about 2 hours. No longer can you get a PhD figuring this kind of stuff out, okay? Because we've got it all automated now. Now, he does trypsin hydrolysis, and remember, trypsin cleaves at lysine and arginine, and he figures out that he got 4 fragments. Fragment 1, fragment 2, fragment 3, and fragment 4. And he figured out that these fragments have this sequence doing what? How did he figure out that fragment 1 had this sequence? You did successive Edmond degradation. But notice the C-terminal is always what? What's that? Arginine? And what about this one, though? That's got to be the very end, right? And I know that's the very end because lysine doesn't leave that as the end. But I also know that because, so I already know the sequence of the C-terminal region. It's got to be leucine, glycine, leucine, leucine, phenylalanine. So he just starts writing that in. Now he's got to figure out this amount, right? He's got to put the other pieces together, right? So that's right. That has to be the last 5 amino acids because trypsin doesn't cleave at phenylalanine. That has to be, and he's got 2 pieces of data that support that. The trypsin data supports that, and his carboxypeptidase experiment confirms that, right? Now we just have to figure out what's in between. So either fragment 2 or fragment 4 have to be the N-terminal side, right? They have to be. And so he does cyanogen bromide cleavage now on these remaining 3 fragments to figure out some more information. Okay? And again, fragment 2 has to be the C-terminus, so now he knows more of the sequence of the C-terminus. Fragment 1 is the N-terminus, that's right. So now he knows this part, he knows that part, and he knows this part, right? And so now he assembles the peptide, what he thinks the structure is, and we actually do this on paper, right? And so now we know what the structure we believe is, and we turn the exam in and hope we get it right, right? Wrong. What do we do at this point? We go back and do the experiment. Cry? Quit that. Stop it. We go back and we do the experiment mentally, right? If this is the correct sequence, the experiments that we did with trypsin, the experiments that we did with cyanogen bromide, all that stuff have to be replicated again, right? So we go back and we think about it. Does everything make sense? Trypsin would have given these fragments. Were those fragments the ones that we saw previously? Yes. That supports the structure. Cyanogen bromide cleaves at the methionines. So we go back and we look at the fragments that we got. Does that make sense? Yes, it does. So we continue on, right? And so we know that the N-terminus and the C-terminus were right. So we always go back and redo the experiment, at least mentally. Actually, we do that now on a computer to go back and verify that the structure is correct. Okay? Today, if you read the chapter in the book, you'll realize that we don't actually do this type of sequencing anymore. That 20 amino acid sequencing would probably take you, using Edmond degradations and everything, would probably take you a week. I can take that sample of that 20 amino acid protein, I can go into my mass spec lab, where I have a mass spectrometer, and I can do some fancy experiments with it that we're not going to talk about in here, and I can have an answer for you in an hour. So a week or an hour? I like an hour too. Yeah, well, that's usually not how it works. Getting paid by the hour kind of goes away at some point in your life. And then it's just you continue to work until you get the answer and you get paid whatever you get paid. That's how life works. So, protein function depends on structure. Everything that we've been talking about, right, in class has been about structure, right? We've been talking about structure till we're kind of blue in the face about it. But it's really, really important for biochemistry because if you change the structure of something, it quits functioning. You die. If your pH changes, no kidding, if your pH changes by a few tenths of a pH unit, you will die because the structure of your proteins will change because they take on different charges. Like charges repel, opposite charges attract. Change the pH, you change all that up, and you'll die, okay? And so alcoholics, for example, they'll drink so much that they'll go into acidosis, and it'll kill them. It's serious business, okay? So it depends on the various amino acids. There's the primary structure, which is what we've been talking about, which is just the sequence. Alanine, blah, 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 phenylalanine. That's the primary sequence. That tells us how the amino acids are linked together. Or that tells us how the monomers are connected to one another, right? But that doesn't tell us the whole structure. It's important for the structure, but you can actually have 2 or 3 peptides with the same primary sequence that actually have overall different structures, okay? So you can have what's called secondary structure. That's the local hydrogen bonding scheme. What kind of hydrogen bonding schemes do we know of for proteins and peptides? What'd you learn in high school? Alpha helix, beta sheet. Those are the big ones, right? And so alpha helices, we have hydrogen bonding between the amide hydrogens in one residue and the carbonyl oxygen in another residue, right? And we can form these alpha helices. So you can see a hydrogen bond here and how that's helicing up. That's just a kind of a local look at it, right? And so you need to have these hydrogen bonds to actually form alpha helices. That's why proline breaks an alpha helix. Because remember, proline won't have an NH. It's a tertiary amide. And so you can't form the hydrogen bond. You'll break the helix, and you can actually go into a random coil or into some other type of structure pretty easily from that. Okay? Here's an example of an alpha helix. In biology, you all like to use these ribbons. That they're not showing you the sequence. What they're showing you is just the secondary structure that's formed from that sequence, right? Because think about it. That's kind of hard to look at, right? Imagine trying to draw that out on a piece of paper, right? I'd go crazy, right? But I could really quickly draw a ribbon, especially with a computer program, right? And this is what's important for the most part, right, is the overall hydrogen bonding scheme. The beta sheet, right? We form these sheet-like structures. So you imagine 2 sheets of paper, one on top of the other. We call this a beta sheet. Again, it's hydrogen bonding between the carbonyl and the NH of an amide, but they form these beta sheet structures that kind of fold in on themselves, and you have these interchain hydrogen bonds between the different things. So that's secondary structure. Tertiary structure is how the protein with all of its regions of secondary structure fold up on itself. Okay? And here we're talking about different types of interactions between the side chains of the amino acids. So for example, if you have histidine and serine, they can actually form a hydrogen bond. They can help these various secondary structures fold in on themselves. You can imagine salt bridging. So if you imagine having an aspartic acid and a lysine, aspartic acid at physiological pH is negatively charged, but lysine is positively charged, so you get this ionic interaction that's occurring. And biochemists like to call these salt bridges. What do we know about ionic bonds? Are they strong or are they weak? They're pretty strong, except in biological media. They're still fairly weak in biological media because you have other salts around, right? And other salts, ionic strength starts to come into play, and you start to get interferences. But nonetheless, we typically think of an ionic bond as being fairly strong. We've already talked about the disulfide bonds, right? So two thiols can come together, be oxidized into a disulfide bond. We can also have hydrophobic interactions. So we have these hydrophobic groups that don't like water, but they like each other. They can start to interact with one another and help the protein fold in on it itself. Where would we most likely find these? On the interior of the fold or on the exterior? On the interior, because they don't like water. Where would we most likely find these? Maybe on the exterior. You could find them on the interior, but they kind of like things on the exterior. They like water, right? So for example, you typically find things like serine residues on the outside of a protein because they like water, right? And so this is an example of tertiary structure. So you can see we've got, what would we call this? And what would we call these lines? Those are beta sheets. And what do we call these loops that we see here? They're just lines. So we have alpha helices, we have beta sheets. What are these just lines connecting everything? No. What are they? Just disordered parts, right? I mean, it's just like a random coil. It'll kind of coil up a little bit, but it's pretty random. It connects everything together. It doesn't have a lot of secondary structure to it. So you can see the alpha helical regions, the beta sheet regions. Okay. Now, a quaternary structure is how these subunits come together and form a larger functional unit. So you can imagine a primary sequence that has alpha helices and beta sheets that folds in on itself, and then you can imagine multiple units of these things coming together to form complicated ion channels or enzymes or whatever the case may be. Large biomolecules. Something like this. That's pretty complicated, isn't it? But that's the quaternary structure. This is hemoglobin. So they have 2 alpha units and 2 beta units that actually come together to form hemoglobin. And hemoglobin is important. Why? Yeah, oxygen carrying, right? Very, very important. So what I want to say here is, how many of you have, maybe your grandma or great-grandma had a kitchen phone with a long wound-up cord? Anybody remember those? Imagine taking that long cord and pulling it straight out. What kind of structure would that be? That would be primary structure, right? Now, as you release it, what happens? It forms secondary helical structure. And what happened to that cord as it hung up there on the wall over time? It started to wrap in on itself. And what kind of structure would that be? Tertiary. And how would we get quaternary structure? You got to have 2 phones next to one another. That's right. And then they would start to interact and get tangled up. Okay? So you can really think of protein structure as nothing more than that old-fashioned kitchen phone with the long coiled cord. Okay? All right. So Friday we review for the exam, right? What do I expect on the exam in terms of this? You're not going to have to solve any unknown protein structures. However, knowing the process of determining a structure is fair game. You need to know Edmond degradation, carboxypeptidase, what the different enzymes do. You need to know the alpha amino acid structures. You need to know how to solve PI given pKa values. Okay? You need to be able to determine the charge state on an amino acid depending on pH. That kind of stuff. Friday, we will talk a little bit about the synthesis of amino acids for about 20 minutes before we get into the review. Okay? We haven't talked about that yet, so read those sections in the textbook, and I'll see you on Friday.